When we computed the formula for calculating a double integral in the last section, we thought about the idea of the region R divided up into tiny rectangles with a function f of xy, the surface above those rectangles, and put together a Riemannian sum, which gave us this double integral, especially as the size of the delta xi and the delta yi approach 0. So when we called dA, if you wanted, in the development, like the area of each of the pieces of R. And so it was either dy dx or dx dy, but that represented by dy dx or dx dy is one way of looking at it, but if we go into polar coordinates, our picture is not the same. So our picture no longer has definitive rectangles, but small sectors of circles, as this picture shows. Hopefully you can see little sectors of circles in there. And the area of each of these sectors is the dA this time, and that can be approximated by treating the area like that of a rectangle. Even though the shape is unusual, this picture, I hope, makes it clear that the formula is similar to that of a rectangle. Okay, here's the idea. If this length is r, right from here to here, and we've chopped this up, then the outer part of this rectangular-like piece, I won't call it a rectangle, rectangular-like piece, has length r times delta theta, where delta theta is the small incremental difference in the angle. And let's say delta r is a small incremental difference in the radius to this piece and the difference to this piece. So I'm going to call this a rectangle, even though I know it isn't. And of course the area of the rectangle is length times width, so it would be r delta theta for our dA. So therefore, when we look at this integral, instead of dA representing the area as a dx dy or dy dx, it will become r dr d theta. We'll need the r because that will give us the length out here, r units, when there's a small incremental change in theta. So it looks like we got an extra variable in our integrand, and we do. So if I were to say use a double integral to find the area of the shaded region, that's this heart here, it's a limaçon. R of theta is 3 minus 2 sine of theta. So here's what we begin. We're just finding the area, so there's no surface above that. If you wanted to think of it as surface of z equals 1, that's okay. And that way it would be a volume, but we're just finding the area, r dr d theta. Now here's how you calculate these limits, and I'll show you another way to do this particular problem at the end of this. But if I started along the positive x-axis and started sweeping around this thing, you can probably see that I've swept out an angle between 0 and 2 pi. That's where these theta limits come from. Okay? Now, same thing, if I swept out with a ray or a line segment through the origin, the outer thing that it touches is the limaçon, right? The inner thing, of course, is, well, there is no inner thing, so there's no inner, like there's not a circle inside that or anything like that. So it would be the inner side just goes all the way back to 0. So the r limits are from 0 to 3 minus 2 sine theta. So when we integrate first with respect to r, we get r squared over 2. That's easy. But our limits of integration, r goes from 0 to 3 minus 2 sine theta, so 0 to 3 minus 2 sine theta, and that goes in there for r, and it winds up squared. Of course, it's over 2, because that's part of the formula for this, or the integrand. And so we get 3 minus 2 sine squared theta over 2, which algebraically, if you multiply this out, it's 9 minus 12 sine theta plus 4 sine squared theta. All that over 2. So, what does that mean? How are we going to integrate sine squared theta? And the answer is, well, we can't integrate sine squared theta, but you may recall, you should recall, from Calculus 2 to integrate even powers of sine and cosine. The trick is to replace sine squared with 1 minus cosine 2 theta over 2. So that's what I'm doing here, right? I'm making that replacement, and now that I've done that, and this 2 and this 4 cancel, this 4 that's out here cancel a little bit, and so I need to integrate this function, and going one step at a time. Oh wait, yeah, actually I'm not going one step at a time, but I'm adding this 2 to this 9 to make it all like terms are in the numerator. And now finally, when I multiply this out, it shouldn't be too awful bad. Actually, I'm ready to integrate it now, so I'm integrating 11 halves minus 6 sine theta, and then this 2 over 2 makes just 1, so minus 1 cosine 2 theta d theta. Finally integrating, I got 11 halves theta. Integral of sine is cosine. Integral of sine is negative cosine, but notice this sign sign changed to a plus. And integral of cosine 2 theta is sine 2 theta over 2. And notice this sign sign stayed the same. And so finally, okay, I need to evaluate that with theta going from 0 to 2 pi. Well, if I put in 0, this is 0. Cosine of 0 is 6. And sine of 0 is 0. So I'll be subtracting that 6 because I put 0 in first. And then I'll be adding, if I put in 2 pi, this is 11 times 2 pi, so that's 11 pi. This will be plus 6, and then minus sine of 2 pi is sine of, actually sine of 2 times 2 pi is sine of 4 pi, which is 0, so that part's 0. So really the only thing that isn't 0, the 6 and the negative 6 from when I put in 0 cancel each other out, so we just get 11 halves times 2 pi, which is 11 pi. Now, just so you know, is that the only way to do this problem? And the answer is no. Because I hope you can see, here's another option. I'm not going to work it all out, but I'll do enough that you can see that we get the same result. Now, instead of going from 0 to 2 pi, if I mess with my limits a little bit, now you got to be extra careful about this. I'm going to go from pi over 2 as a lower limit to 3 pi over 2 as an upper limit. Same function here, but notice why I couldn't go from 0 to pi, because then I would only be calculating the area of this piece that's above the x-axis. And what I'm trying to do is capitalize on the symmetry of this thing. This heart-shaped object is the same on the left side as it is on the right. But if I were to say, well, what are the angles I would be sweeping out from here? It would be from pi over 2 to 3 pi over 2. And so if I calculated this, you know, in other words, I'm finding this half only and then doubling it, that should give me the exact same result, and I do want to show you that you do. Remember, our answer for this when I did it the other way was 11 pi, and here you also see, I'll just let the computer evaluate it, here you also see 11 pi.